The M16 and AR15 has been the American military's standard service rifle since the late 1960s and has served in every conflict since Vietnam. For my FEA project, I will analyze one of the most key parts, the bolt, which holds the pressure in the chamber. This rifle design features a rotating bolt with 7 locking lugs. The bolt's purpose is to chamber the cartridge and keep it locked in place during firing. These locking lugs are rotated into a locked position in the barrel extension. These locking lugs are responsible for keeping the immense pressure of firing in the barrel. When I say immense pressure, I mean it. A chamber pressure curve can reach up to 60,000 psi, as seen here. I took this data and extrapolated it to Excel to create a table of values over time. Then taking the technical data package for the M16 rifle, I was then able to create the bolt in SolidWorks by utilizing this nice and easy 2-page engineering drawing. After an easy 5 hours in SolidWorks later, I get this part, which is the bolt of the M16 rifle. As you can see here, there are 7 locking lugs on the front, which are responsible for holding the bolt in the chamber under that immense pressure. Now to import this part into Abacus. I've had some trouble importing a SolidWorks part, so I use an IGS file. So save this as an IGS file, and then in Abacus, you don't need to create a new part. You can just hit File and Import, and then search for the IGS part and where you saved it using the IGS file type. Once this part populates to Abacus, I get a poor geometry warning. For better or for worse, I ignore this, as I have not had any issues. For the rest of the Abacus setup, I must choose a material. I use material of S7 steel, which is the actual material used in a bolt. Because I designed this part in English units, I need to make sure I use English units for the Young's modulus and Poisson's ratio, both of which I found online as properties for S7 steel. I create a section using the defined material and then apply this section to the part. Next, the part is added to the assembly in Abacus. For this model, I create a first static step. This is the base for my boundary conditions. The second step is a dynamic implicit for my pressure curve. This step has the same time length as my pressure data. The third step is another dynamic implicit step. I make this 0.25 seconds long to view what happens after the pressure has been applied and then released. After the steps, I then define the loads and displacements. The first displacement boundary is the back of the locking lugs. I then select the 7 back faces of the locking lugs on the bolt. These lock into the barrel extensions and cannot move, so I imply that they cannot move in the X, Y, and Z direction, and then they cannot rotate. This creates them permanently static, as they would be, or as I am going to simulate they would be in the firearm. I now need to simulate a load of the chamber pressure. I use this by using a pressure load on the bolt face. The bolt face is where the cartridge rests and what would experience the opposite end of the 60,000 psi that the chamber pressure experiences. Now to input the chamber pressure, I do a magnitude of 1, and then I do an amplitude or a table, and then I can just copy and paste from the table into that column and row of the time and the amplitude. With this inputted, I can be okay, and that concludes all my loads. I then mesh the part. I've played with this a few times, so I choose a slightly finer meshed part. Because this part is so complex and I need so many nodes, I'm doing this on a school computer as to not be limited by the 1,000 node limit of the Abacus on student. You need to use tetrahedral elements, and then I applied them throughout. Querying the mesh, I find I'm using 76,000 nodes and over 47,000 elements. After creating, submitting, and running the job for over 20 minutes, I can now see the results. Running the initial results, I have the deformation scale set to 1. This doesn't let us visually see the deformation in any other method except through the color scale applied to the part. Pay close attention to the step and step time in the top right. Notice the pressure curve being applied to the bolt face in the pressure step and the subsequent deformation in the aftermath step when there is no longer pressure being applied. Some of this violent deformation is due to the pressure curve data. The pressure curve is not complete through zero pressure. Using the data provided, the bolt's face goes from experiencing 20,000 psi to 0 almost instantly. Although this is not completely the experience of the physical part in a real firearm, the pressure does drop off very quickly after the bullet has left the barrel, making this simulation not completely unrealistic. We can change the deformation scale through the commands of option, then common, and then entering the chosen value, in this case 1 million. This allows us to see the deformation travel throughout the part, as seen here, at a scale of 1 million. Now viewing the von Mises stress in the part, we can see the deformation travel throughout the part coupled with the stress color pattern. Now zooming into one of the most key aspects of the part, the locking lugs, we can see how well this part is designed. All the chamfers and fillets on all the parts allow that the stress is neglected and not concentrated in all the corners. The final analysis of my FEA project is to view this part as a cutaway section. The View Cut Manager allows us to choose the orientation and location of this section view. Doing this lets us see the stress from different angles, especially because the part has many interior holes that might be stress concentrations or large areas of deformation.